Okay, guys, so we'll start the class. We have basically to finish the previous chapter. We did basically the existence and then local uniqueness. The only thing we also did the everything goes, and then I have to basically get rid of some concepts that you need. I'm gonna go fast on this part. So first of all, uniqueness, right? So in general, so you have a practical implementation of the general equilibrium model. You would like to have essentially a one equilibrium. So essentially, why do you like that? As we discussed in the previous class, having two equilibriums is sometimes hard, and you have a good justification how to think about them. It's going to be hard. So in general, if you study macro models, most things that you see, they're going to exhibit one equilibrium. So given an economy specified by the constant returns to technology Y, and the aggregate excess demand function of the consumer set, a price vector P is a well-rational equilibrium price vector, even only if you have these two conditions. So essentially, you have that P times Y is less than or equal than 0, and Z is a feasible production. Is feasible given the production. And then we're just going to prove essentially this thing, which says that P is a well-rational equilibrium, then two follows from market clearing. One is a necessary condition for profit maximization, as we remember with this constant returns technology, zero profits, and 1 and 2 hold, then essentially the optimal demand with endogenous budget has to be optimal for all individuals, and then you have to be such that whatever is produced is equal to whatever is in the excess demand. And then you can just verify using Walras law. So then using this excess demand, we can impose the weak axiom again. So the weak axiom for excess demand function. So the excess demand function Z satisfies the weak axiom real preference if for any pair vectors P and P prime, we have that if the two excess demands are different and the multiplication of P times Z of P prime less than or equal than 0, this implies that for another P prime, multiplied by ZP, this is strictly greater than 0. Now, why do we care about this weak axiom condition? So essentially, this weak axiom condition will imply some form of uniqueness, global uniqueness. So suppose that the excess demand function is such that for any constant returns technology, Y, the economy formed by Z and Y has a unique normalized equilibrium. So remember that because of homogeneity of degree 0, we cannot have a unique price that describes the economy, but we have uniqueness up to ratios or up to normalization. So remember that. So the only thing that you're going to recover uniqueness is ratios of prices. Do you understand? So for instance, in any economy, if you say the economy is globally unique, it means that the ratio of apples to oranges is unique, right? Then the scale of the prices can be in different units, right? Because of homogeneity of degree 0. So it can be, for instance, you can have $10 for apples and $5 for oranges, and then you can have $100 for apples and $50 for the other fruit. So essentially, you can scale this to any positive scale, right? So uniqueness is only up to normalization. Now, suppose that excess demand Z is such that for any constant returns convex technology Y, the economy formed by Z and Y has a unique normalized equilibrium price vector, then Z satisfies the weak axiom, okay? The thing that we just defined right now. Conversely, if Z satisfies the weak axiom, then for any constant returns convex technology Y, the set of equilibrium price vector is convex. And so if the set of normalized price equilibrium is finite, then there can be at most one normalized price equilibrium, okay? So in other words, remember that because of the previous thing that we studied, when the economy is regular, right? We already concluded that you have finite number of equilibria, right? If you are regular, then you cannot have infinite number, right? You can only have a finite number of equilibria. Now, if you combine this with weak axiom, then you're gonna get, in fact, that you have a unique equilibrium if the weak axiom holds. So now, this weak axiom condition is a sufficient condition for uniqueness. So for instance, if you check it, you know there is a unique equilibrium. And then essentially the proof is a bit simple, so I'm just going to skip it, but you can read it. It's essentially 2 sentences. But so the question should arise in your minds of how to impose it. So how are you able to impose this weak axiom condition? So remember that the weak axiom condition on this general equilibrium setup is a condition that is implied on the excess demand. So again, if you're writing your own macro model, so you become a macro person, you become a consultant, how in the world will you impose enough restrictions on your preferences and technologies such that you get a unique equilibrium, right? This is what I'm going to provide next as an answer. So one sufficient condition that is of course different from the weak axiom, but is easier to impose in terms of preferences, right? Is what is called the gross substitute property. So the gross substitute property says that this function z has the gross substitute property whenever p prime and p are such that for any good L, p L of prime is strictly greater than pl, and then pk prime is different from pk, from other good different from L. And then we have that zk of p prime is greater than zk. So what do you see here? Essentially, you have two goods that are competing, right? So for instance, apples and oranges. So L is apples, K is oranges. And then if the price of the substitute increases, right? So in the PL prime situation, so you have way more expensive apples, right? Then the demand for excess demand for oranges should increase, right? That's what this is saying. So this is a substitution property, right? But why it's called gross? Because remember that substitution in these models is very complex. So here we're just saying, so we don't care about complexities. In general, income effects, you're going to have a gross substitute property, right? If the price of your competitor rises, of course, the demand of the K good is going to increase. Okay. Any questions about this property? So it's very simple, right? Moreover, Z is homogeneous of degree 0. If Z is homogeneous of degree 0, we also have that the good that its price increase also decreases, right? ZLP prime is less than ZLP. In other words, the demand or excess demand of the apples, which its price increase, is lower than before, okay? The important thing about the gross substitutes is this part. So any questions about this? So this is the property, the gross property, gross substitute property, and this is essentially what all macro uses. So turns out, right, that if you Google this, essentially, right, utilities such as Cobb-Douglas, CES, that are super popular in macro, satisfies the gross substitute property, okay? So obviously we're talking about uniqueness, right? So now we say an aggregate excess demand function Z that satisfies the gross substitute property has at most one exchange equilibrium. That is, Z of P is equal to 0, has at most one normalized solution, okay? The proof. So we have to check that ZP is different from ZP prime, cannot occur whenever P and P prime are price vectors that are not collinear. What is collinearity? So it's basically a scaling of another vector, right? So now by homogeneity of degree 0, we can assume that P prime is greater than or equal to P, and PL is equal to PL prime for some good L. Now consider altering the price vector P prime to obtain the price vector P in L minus 1 steps, lowering the price of every commodity K different from L, one at a time. Now, by the gross substitution, the excess demand of good L cannot decrease in any step, right? Because it's the competitor's price. And because P is different from P prime, it will actually increase in at least one step. Hence, you know, ZL of P is strictly greater than Z of P prime, which means, right, that they cannot be in equilibrium because the original ZP was equal to 0, right? So the ZP prime has to be out of equilibrium. So the gross substitute property is a sufficient condition for uniqueness, okay? So how it works? Essentially, you have a model, right? You're able to impose the gross substitute property. You don't have to do anything more. You know there's a unique equilibrium, so you don't have to look for any other, okay? So is that useful? For sure, right? So when you become a researcher, right, in the second year, then what will happen is that you will possibly build a very complex model. Have you seen the models by macro people, especially, you know, job market candidates are very involved, right? So they have different kinds of consumers, different types of producers, a lot of goods, you know, a lot of elasticities, a lot of complexity. Now, how people solve those models? They put it in some software, right? In old times, people use MATLAB. Now they use Julia, right? Whatever software is the one that people use. You put this system of equations there. It's a very complex nonlinear system of equations. Then what do? You start, running an algorithm to solve this nonlinear system of equations, right? Usually, because it's not complex, very complex, you use some stochastic method, right? And then you leave your computer run for several weeks. And after those weeks, you finally go and find your computer still, and you say, oh, wow, my model has been solved. I cannot procrastinate anymore and be wandering around, right, during the cafeteria and stuff. And then, I can start writing. But, the one question comes to your mind and you say, look, so this team found an equilibrium. Is there another? Do I have to wait for other 2 weeks to find all of them? And what about if I have 100 ones? Have I found all of them? Well, the answer, lucky for you, is that you impose gross substitute by using an appropriate parametric family. And you know that thanks to gross property function, there is no need to search for another one, okay? So that's actually something useful. And again, in the core exam, so for instance, this question has appeared historically. So they say, oh, verify the gross substitute property here. So is there a unique solution? So yeah, it has appeared. It's not hard to understand, but you have to know. And it's useful, again. Now, important thing, gross substitutes and work are different conditions. Both imply uniqueness, but they don't imply each other, okay? So these are alternate conditions that are logically independent that both imply uniqueness, okay? So if you have weak axiom, then you have a uniqueness property. If you have the gross substitutes, you have uniqueness. If you have gross substitutes, you may fail the weak axiom. If you have weak axiom, you may fail the gross substitute. So this shows essentially these two things are only sufficient, okay? They are logically independent among each other, and then both imply the uniqueness property. Any question here? So all in all, what we have learned this time is that getting uniqueness requires way more restrictions, right? You need to add more restrictions to your model in order to recover local uniqueness. So local uniqueness is not something that comes naturally to general equilibrium, right? It's not at all the natural thing to happen. You have to impose these conditions, okay? Now, again, so why do we want uniqueness? Well, essentially, if you are delivering a product, right, using general equilibrium, you would like to make a unique prediction. Again, so think of yourselves in your future professional careers, right? And then, this is something people do, right? For the World Bank, for the UN, European Union, Council, all of them do general equilibrium analysis. Thanks to Trump, he destroyed free trade, right? And now we have to reanalyze why free trade is actually good or not, right? So remember in the 90s, everyone said, oh, don't study trade. That's done. It's obvious that we should do free trade. Just leave it there, right? What are you asking? Now we're back to the question, what are the costs and benefits of trade? So the most important general equilibrium models are actually in the study of trade, international trade, right? So essentially, everyone there does general equilibrium analysis. And the reason is because, when you have trade, you have one market, right? So you are exporting, strawberries from Canada to other places. Now, what are the impacts of other markets related to the strawberry market, right? So it's a lot of interconnected markets that are going to be affected by by opening a particular market, right? If you remove tariffs on strawberries, then possibly, blueberries are going to be impacted, but not only that, also the market of milkshakes, right, in the summer, and then some restaurants are going to be affected, and then some salaries, right, and so on. So that's the idea of general equilibrium, is essentially trying to capture this butterfly effect, right? Do you know what is the butterfly effect? So it's this idea in the kind of 80s, because of global warming, and there was a discussion about what's called chaotic systems. And the idea of the butterfly effect is that some systems, such as the weather, are chaotic in the following sense. So small changes in initial conditions can cause big changes in the broad system. For instance, the idea was if a butterfly, was flying and moving her wings a lot in Brazil, there may be a hurricane, right, in the Boston area, right? So the idea is that maybe a small change in some part could have impacts in very far away because of a very interconnected system. Now, it turns out that general equilibrium actually is one type of mathematical type of chaotic system. So it's very easy to generate these butterfly effects in general equilibrium. So there are a lot of papers by macro guys trying to study this, right? So how small changes in one market causes big changes in other markets. But of course, that's easier said than done. In general equilibrium mathematically is super hard to tame, to understand, to estimate, to calibrate, to in general be able to implement seriously. So right now we're just learning the very abstract concept of general equilibrium, right? And then, as a practical thing, when you do consulting or you work for someone, sometimes it's ideal to have a unique prediction, right? Because that's easier to understand and defend, and you can study scenarios, right? So again, I'm not telling you marry to unique equilibrium. No, I'm telling you it might be something you need to do just because of sanity, right? If you're trying to explain to policymakers, you're not going to explain to them the 100 equilibriums, right? Barely they will understand. So you have to be clear. You have to be, understandable. And if you don't explain things clearly, you lose credibility, right? So this is something that might be even good just for teaching purposes, okay? And remember that as a researcher, you're going to be also a teacher, teaching about your research, right? Now, having said that, right, so we only know sufficient conditions for uniqueness. Of course, uniqueness does not arise naturally, okay? Only under these sufficient conditions you get it. Else, general equilibrium is known to generate very weird equilibrium, right? So that's essentially the nature of general equilibrium. Now, okay, I'm gonna go deeper into this uniqueness versus other later on, but right now I have to introduce this concept, the core. So the core is a popular in core exams. The name is not related. This is a different core from the core exam. I'm gonna explain this idea to you. And this is a great idea, Edgeworth, the English mathematician, economist, social scientist, genius, he invented this concept. So he had his Edgeworth box and he was saying, look, okay, so let's imagine you have an exchange situation. So how people are gonna essentially arrive to equilibrium, right? Remember, we don't have a theory about prices. So the Edgeworth box just tells us, compute this thing and you'll get a price. But in real life, right, in the experiment, how do we imagine trade arises? How do we imagine prices arise? It's very hard. We don't have a theory about it, right? The closest to the theory is this of formation of prices is this creation by Edgeworth, the notion of the core. So I'm going to tell you. So formally consider an economy with I consumer. Every consumer I has consumption set R, L plus, an endowment vector omega I, weakly positive, and a continuous, strictly convex, strongly monotone preference relation, the symbol of preference sub I. There is also a publicly available constant returns of convex technology, capital Y. For example, it could be just the predisposal. And now recall that if an allocation is feasible, if it will satisfy the following equality, the summation of all consumption is equal to the all production plus endowments. Now we're going to define a coalition. So a coalition is a subset of consumers that is not empty, and essentially, a coalition, just a subset of individuals, can improve upon or block a feasible coalition if for every individual inside the coalition S, we can find a consumption vector xi that is strictly preferred for every element, for every member of the coalition. And then essentially this coalition is feasible for the coalition. In other words, the summation of the xi over the coalition belongs to the production of the economy plus the endowments of the coalition, okay? So now, essentially what this is saying is the following idea. So imagine Edgeworth creates a larger experiment. So I take all of you, 12 people, and then I put you in a laboratory setup. I tell you, okay, we're gonna give you some endowments. And now essentially you're going to decide how you're going to produce an outcome, an allocation, right? And then, you know, the natural thing to do is you start making coalitions, right? Have you seen reality shows? The Big Brother is a little bit old for you, but you know, other reality shows. What's the first thing people do? Survivor, right? So alliances, right? So they start looking for allies, right? So I'm looking for people that are like myself, like an ally to, right? So this is a coalition. It's a group of people that they can put together their resources and say, okay, we're out of this thing. We're going to create our own group, right? So that's a coalition, okay? So now a coalition can block an allocation if they get together, pool their resources, and then essentially they can say, look, whatever you're proposing to me, right? I don't want it because I can create my own allocation given my resources inside the coalition, right? So the blocking property says if they can find a consumption that is preferred for everyone in the coalition and is feasible, okay? That's the notion of blocking an allocation by coalition S. Now, this means that a coalition S can improve upon a feasible allocation X star if there is some way that by using only their endowments and the publicly available technology, they can create a better allocation. So now, what is the core? And this
Victor,
is the
one
idea.
question.
Yep.
Do you explain the second condition in the definition?
Yeah, so it just says that whatever you consume in the preferred allocation, the summation over the coalition, right, Xi over the ZS, has to be feasible for the coalition. Remember that the technology is publicly available, so everyone can use it, right? So this is non-rival. So that's why, the same way for everyone, plus the endowments that belong only to the coalition, right? So it's just a feasibility condition for the coalition, given a publicly available technology, okay? Okay, so this is non-rival. So the fact that they use this technology does not prevent other coalitions from using it, okay? So it's like the garbage can is an example of publicly available technology, right? It's non-rival, okay? So a counterexample of this would be, for instance, depletable resources, right? You have a gold mine that has certain level of amount of gold, and then, you know, if they start digging this non-renewable resource, then this will be a counterexample of this. We're talking about a free publicly available technology, non-rival, okay? This is what we mean by this, okay? Now, the core property, we say that a set of feasible allocations X star has a core property if there is no coalition of consumers S that can improve upon X star. So in other words, something is in the core of the economy. If there is no coalition of consumers, remember that the coalitions here that we're considering are all possible coalitions, all possible subsets of consumers. So this property, super strong, is requiring that out of the 12 of you, nobody blocks this individually. So for instance, Amat cannot block it, right? Irina cannot block it, Martin cannot block it, Zhao cannot block it. So none of you individually will block it. And not only that, then every couple will not block it. For instance, Amad and Martin will not block it if they get allied together. Irina and Zhao will not block it, right? So, and then every triple will not block it. And you got the idea. But essentially, you have to check for all coalitions. So how many coalitions there are in 12 people? So 2 to the power of 12. Yep.
Sorry. Yeah, so just one question. So you said the case for 1, 2, and 3. And does it go on or is it just at 3? So
that's it. It goes on. It is for the whole power set. So the total number of coalitions in this class would be 2 to the power of 12 minus the empty set, right? So it's essentially a very, very large number. So, and then checking the core essentially means that any possible combination or alliance, right, cannot block this thing, okay? So the core property is essentially super, super strong, okay? And remember, this includes the coalition of the 12 of you. So you unanimously cannot block it, okay? Individually cannot block it, and everything in between, okay? So this property is super strong. Now, the core is a set of allocations that have the core property, right? So of course, there can be more than one allocation that has the core property. So the core in general is a set, okay? Now, important thing, for the case of 2 individuals, so 2 consumers, the core is equivalent to the contract curve of the Edgeworth box, okay? So you remember what is the contract curve? It's essentially all the set of Pareto allocations, right? So the tangencies between the two indifference curves in the Edgeworth box that we discussed. So another name for this is called the contract curve, right? So the set of Pareto allocations in this Edgeworth box, right? When you cut this set of Pareto allocations from all the allocations that are not individually blocked, remember that each individual in an economy has an endowment, right? So no consumer that has local non-association will accept, so monotonicity. Here we need monotonicity. So no consumer that is monotone will accept something smaller than their own endowment. Do you understand? So under monotonicity, if you're given 10 apples, 10 oranges, you will never accept 9 apples, 9 oranges, right? So you're not giving away apples and oranges. So this is a strongly dominated in the vector sense allocation. You're not going to accept it. So all of these allocations that are dominated in the monotonic sense, they're going to be individually blocked. And now, if you take essentially remove out of the Pareto set the allocations that are individually blocked, then you essentially get the contract curve, right? So in other words, for the case of two individuals, how many coalitions do we have? We have the singleton coalitions, so individual 1 alone, individual 2 alone, right? And then you have the unanimity, right? Individual 1 and 2 together, right? So things that cannot be blocked by everyone, right? Those are Pareto, right? But now things that cannot be blocked individually, right? And then you get essentially the core, okay? So now for two individuals is super easy, right? Now, how do you compute it, for instance, for 3 individuals? How do you compute the core? So you have to check essentially things that are not blocked by individual 1 alone, individual 2 alone, individual 3 alone. And then you have to break your economy into economies of size 2, right? You combine individual 1 with 2, individual 2 with 3, individual 1 with 3. And then you find the contract curve of each subset of the Edgeworth box, right? Which is itself a 2-dimensional Edgeworth box. And then from those allocations, you check those that are Pareto efficient, hence not blocked by the coalition of size 1, 2, 3. So this kind of algorithm can be done, sequentially. And of course, if you have 4 people, then it will be super hard. Now, for you, luckily, I haven't seen until this day a core question that asks you to find the core for more than 2 individuals, right? So essentially, it's not that hard, but you have to know the concept, right? Okay. Now, here comes the punchline. So I have prepared you for the core exam, but the interesting thing is this. Any well-rationed equilibrium allocation has the core property. Okay, so this is the cool thing about all this discussion. Turns out that if you have a well-rationed equilibrium, right, that is coming from pure exchange, right, then this will have the core property. Okay. So in other words, the well-rationed equilibrium, or the set of them, will be a subset of the core allocations. So remember, the core allocations are a set. The core is a set. Any well-rationed equilibrium, right, can be one or many, is going to be inside the core. Okay. So let's see why. So let X be a well-rationed allocation with a corresponding price equilibrium P. Consider an arbitrary coalition S, and suppose that the consumption Xi for all individuals in the coalition are such that Xi is preferred strictly for the allocation that is a well-rationed equilibrium X star for every individual in the coalition. Then it has to be that because of the strict preference, that this is also strictly non-affordable, right? For every individual in the coalition. And therefore, if I compute the multiplication of prices times the summation of the Xi in the coalition S, is going to be above the summation over the endowments omega I. But then Xi for all individuals in the coalition is not feasible. So coalition S cannot block X star. So in other words, the existence of course, a well-rationed allocation means that the allocation that you're being offered, X star, is already maximum, right? It's the maximum according to a budget. So that means that whatever allocation that is strictly preferred is going to be non-feasible. So all of this is about feasibility, right? So as I told you, the decentralized system given by the well-rationed equilibrium essentially ensures that there is no waste, right? So you're already picking the most preferred alternative given the resources. So no coalition can improve upon the duration equilibrium. So yet again, this is a cool thing to have. Now, so why was Edgeworth thinking about the core? Well, really, as I told you, the general equilibrium, the idea of a price, does not tell you how the price arises, right? So for instance, using the core, you can actually create an algorithm inside the experimental setup where I essentially ask, I form all coalitions. I tell you to communicate among the people in the coalition. And then I ask you to tell me if, as a group, you can block any given allocation, right? If I run this algorithm long enough, I will be able to find, all the allocations that are not blocked by any coalition, and this will constitute the core. Turns out that the well-rational equilibrium is going to be inside the core. So in a way, by running this algorithm of trying to see which coalition blocks any allocation, then I can essentially find the well-rational equilibrium. Okay. Now, this is the part that we're not going to prove. The proof is in Mascolel we are interested in. This is beyond the interest of the class. So remember that the relation is well-rational allocations are a subset of the core. So that means not all allocations in the core are well-rational allocations. Now, when the number of individuals goes to infinity, and this is achieved in a very precise way by using a concept called replica economies. So essentially you take the Edgeworth box of size 2, and then you copy it exactly, and you create an Edgeworth box of size 4, right? And then you copy it again, and you have an Edgeworth box size 16, and you do it again and again. And essentially you end up with a number of individuals going to infinity. As the number of individuals in the replica economies goes to infinity, the core converges to the well-rational allocations. So in other words, this is a bit artificial, but the idea is that the difference between the core and the well-rational allocations is just that you don't have a continuum of agents, right? If you have enough of agents and then you can form infinite coalitions, then essentially they will refine sufficiently the core allocations that they will be exactly equal to the well-rational allocations, okay? Any question here? Okay, the proof is beyond the scope of the class, but you can check it in Mascolel. It's kind of a cute proof. You can read it, okay? The idea is that the core will converge to the well-rational equilibrium as the number of consumers goes to infinity. So the core is essentially a theory of formation of price, if you want, right? So by running these blocking coalitions, then essentially you see how a price can arise. So, imagine in the world of Uber, right? So Uber, taxis, riders, so drivers and riders. Now you essentially allow, all possible group of, groups or consumers, taxis, only taxi drivers, only riders. They get together in all possible combinations, and essentially after they're blocking all of the possible coalitions, then you refine the well-rational equilibrium, right? So if any group can block, an allocation, then this is no longer a well-rational allocation. So this tells you also something very nice about the market, right? So think about the problem of allocating, resources like here with endowments. So imagine, you form a new society, and then you survive in the Noah's Ark, right? You were given some allocation of food, water, and so on. And now you get to go and try to form a society. Now then, somehow they start deciding how to allocate things. This is telling you that if you use a market price system, right? So a well-rational equilibrium, then you're essentially politically stable, right? Because being a well-rational allocation guarantees that nobody wants to create their own sub-society, right? Essentially, you get together, pool your resources, and get out of there, create your own town, right? So, if you have a market allocation, then people will be doing their best already. And they can essentially, the market allocations under the well-rational equilibrium have the core property, which is a form of political stability. So no one inside the economy can pool the resources and get out, right? So, for instance, everyone knows the case of Spain and Catalonia, right? Barcelona. They went out of Spain, right? That's essentially what means coalition blocking. So they say, I don't want your allocation. Madrid, the capital, is giving me this amount of money, right? I think it's below what I give, right? So I want out. I'm going to pull the resources of the people in Catalonia. I'm going to create my own country, right? That's what I want to do. That's essentially the coalition blocking, right? Getting out of the country and creating your own, okay? An allocation that is a market valuation equilibrium has the property that you cannot block it, okay? You cannot block it. So of course, if we dig into the Catalonia example, they are angry about the centralized, politicized redistribution of taxes, right? So obviously it's not a market outcome, right? So this is yet another nice property of the valuation systems, okay? So again, if you survive apocalypses, right? Remember that price systems are still good. So again, it's a stable, politically stable way to assign things. Now, of course, this sounds very nice, but it's ignoring something very important. And what do you think is missing of this nice theory? So obviously, power, right? So essentially, right? If you think that these economists are assuming that nobody has power alone, right? So first, imagine you are back to the times of when we were cavemen and cave women. So who won? Really. So is it really that people could form coalitions, or there was a one big caveman that was the best fighting, and then essentially became the king, right? And this kind of cases essentially means that some people have more weight than others, and if this king caveman block the allocation, then nobody can do anything about it, right? So so this is ignoring power, right? So all of this is assuming that everyone is on a level ground, right? Everyone has one vote somehow, and they can of course become allies, but nobody has extra power, right? If you have an even distribution of power, which in some cases you can actually model it as endowment. So remember this, power can sometimes be modeled as endowment, right? So just by taking care of modeling power or introducing power, then things get a little bit more realistic. But essentially, all of this is ignoring power, right? And when people have power over others, right, then market systems do not make sense, right? One key case, for instance, is the case of the slavery, right? So there are some people forcing others to work, right? So then there is no way to talk about wages or actual compensation of marginal products. So there is power of one individual over others. So remember, all of this is done in the void where power is equally distributed, okay? Now, if you introduce power inside the modeling as part of the endowment, then you can do something about it. But right now, this is kind of assuming way that, okay? So what I told you, works under the assumption that power is somehow evenly distributed. Okay, so let's make a stop. And then we're going to move finally to chapter 14, which is really cool. It's testable restrictions on the equilibrium manifold. And essentially this chapter, it's going to be about how we can study general equilibrium from a revealed preference perspective. So at this stage, I hope some of you are missing the clean analysis and the clarity of the generalized axiom of revealed preference and the Afriyat's theorem, right? So we have said a lot, but a lot of it has been a little bit unsatisfying because remember that all of the things we have studied in general equilibrium were we are studying this model. We want to know whether it's internally consistent, right? Existence. We want to know under what conditions can we get some form of uniqueness, right? But have we say anything scientific about it? A scientific model, right, has assumptions but also produces predictions, right? And then these predictions have to be tested against data, right? Have we done anything about that since we started the second part of the class? Have we made any prediction so far? What do you think? So, radio silence. Yeah. Someone?
I don't think so. I think it's been mostly theory throughout with a couple applications here and there. So No predictions jump to mind for me.
Yeah, and so, but that's weird, right? Because supposedly we're studying social science, we're doing scientific theories. So where are the predictions of general equilibrium, right? So again, I'm going to ask you. So general equilibrium, as everything else, as any scientific theory, is sort of a function, right? What are the inputs of general equilibrium? So who remembers this? And what are the outputs? So the inputs of general equilibrium are preferences. What else?
Budget.
So endowments,
Endowments.
endowments, more than budget sets, and
Technology.
And the production by
Technology.
the
Great. So preferences, technologies, and endowments, right? Those are the three inputs. And what is the output?
Prices and relative prices and allocations.
Exactly. And allocations include consumption vectors and production plans.
Mhm.
And then, of course, price. That can be one or many, right? But at least one price. Okay. So inputs are endowments, right? And you assume you know preferences for simplification, right? Assume you know preferences and technologies, right? That's part of your estimation. You do your metrics and you recover preference and technology. Now, you have new endowments, right? Endowments are changing. And then you want to predict prices and allocations, okay? So let's go back to the experimental setup. So you run your own general equilibrium experiment. You put two individuals in an environmental setup, in a room. And then, what do? You give them inputs, right? So they have their own preference and you assume you have already elicited their preferences, right? Now, once you have done it, the only thing that remains to do is fix an endowment. So that's the input, right? And then what do? So you predict using general equilibrium a price and an allocation, right? And then what? So if you have produced a price and allocation, then supposedly, if this is a scientific theory, there should be some predictions of these actual prices and allocations. So in general, if I have another Azure box where I change again the endowment to a new level, right? And then I see what happens in terms of prices and allocations, then I can use these two observations, right? So endowments coupled with prices and the second Azure box endowment and the second price can be used to test whether these outcomes and inputs come from a general equilibrium situation. And this is essentially what we want to do now. So we want to do finally testable implications of general equilibrium and do some predictions. Predictions on what? On prices, okay? So yet again, as I told you, what a lot of macro people did back in the 90s and in the 80s and so on was price prediction. Why? Because inflation was all around us. Inflation was a big issue, so changes of prices usually upward, right? Was the main concern of a lot of economists. So a lot of economists try to predict the price changes. Do you understand? How do you predict price changes? Using general equilibrium. So people back in the day used these very simple linear versions of general equilibrium called bars, right? Vector autoregression models that when they were done by economists, they were called structural bars because the structure came from system of equations associated with equations according to each market, right? So essentially it was a linearized version of general equilibrium. And then you use it inside a statistical model to predict prices, okay? From what? From shocks to the economy. And then what you did, as that was mainly all economists back in the day, they tried to predict price changes, okay? So we're doing the same, but to a very high level, right? So essentially we will produce a very non-parametric prediction of prices given endowments or given incomes, okay? So before starting this episode, right? The podcast, this chapter, so let's take a break. So we are able to rearrange essentially 5 minutes as usual, and then I can take some water and also set up the iPad, okay? So I'm gonna just stop, pause the recording. Okay. So welcome to chapter 14, testable restrictions on the equilibrium manifold. So that's exactly the title of the paper by Brown and Matsky, okay? So Professor Donald Brown and Professor Rosa Masking, I think Rosa went to, I don't remember where she studied, but Dr. Donald Brown was in Yale. Rosa Masking, she's a econometrician, now econometrician, by the time she liked microtheory. So again, both people that are geniuses, they do reveal preferences, and at some point they got tired of this nonsense of anything goes. Schoenstatt, Mantel, de Breu that we discussed. That there is no predictions of general equilibrium. So we study, a lot of chapters in Mascolel, and then your scientific theory has no predictions. Bummer for sure, but also very not scientific, right? So scientific theory should have predictions. So what's up? What happened with general equilibrium? So the issue, as I mentioned in the Schoenstatt-Mantel de Breu theorem, that anything goes, was based on the assumption that endowments did not change, right? So remember that general equilibrium is a machine, right, that maps endowments, parentheses, preferences and technologies, to prices, right? So now, if you don't change the input, how are you supposed to see whether a function has certain properties, right? Do you understand? So the input of this machine is endowments. So Schoenstatt-Mantel de Breu said, let's assume endowments don't change. And why did they do that? Well, essentially, people are subject sometimes, even they are super smart, right? Schoenstatt-Mantel de Breu were geniuses. But at the time, what was the macro data people have at hand? They had just a time series of a country. So is a country changing their endowments every year? Not really, right? So, I'm from Ecuador. So we have been endowed with oil, minerals, and a lot of bananas, right? That's our endowment. So if 2020 and 2021, do we get to change too much the size of bananas that were allocated? Not really, right? So in general, that the scientists were subject to that idea. So endowments are not changing much, right? They are
when you
fixed.
say that we are trying to predict prices conditional on changes on endowments, do we also refer to changes in preferences and technology or not in a
No.
more general framework?
No, that's the whole
Why
thing.
not?
Preference and technology have to remain the same. If they are changing, then you have to modify these things, okay? Remember in the Afriat's theorem, what was the whole assumption? That utility never changed, right? Your budgets were changing, right? But your utility function remains the same. It's a function, of course, but it does not change. Remember that the fact that a function does not change gives you flexibility, because a function can be evaluated at different inputs and give you different outcomes, right? So it's not such a big of an assumption, right? When I'm saying, preference don't change, it means that the preference function, the preference relation, the utility function does not change, right? Does not mean that the utility value does not change. Obviously, it can change because it's evaluated at different inputs, right? Do you understand? But here, the technology assumption for sure is restrictive, because we know right now, we get so much technological change, right? iPhone 12, iPhone 13, they're almost the same, right? So much change. No, just kidding. But we know there are technological changes that may alter this assumption. We're assuming technologies remain the same, and also we're assuming preferences remain the same. This is the key assumption. So essentially, right now I'm going to give you a theory. It's not a grand theory. It's a very specific theory. It's a theory of this Edgeworth box that we imagine running an experiment in a room, right? Where I put two individuals. They have the same preferences because there are two fixed individuals. And then I change their endowments. And every time I change their endowments, I record what price did they agree upon, okay? And then I get this data for as many changes of endowments I do. And I get a data of endowments and prices. And then I check whether this comes, in fact, from general equilibrium exchange. So in fact, if every individual inside my experimental box was utility maximizing subject to their endogenous budget constraints and market clearing. Okay, do you understand? That's the theory I'm going to propose now. Now, this is a humble theory, but at least it's a scientific theory, okay? And it's way beyond the anything goes, okay? So random masking present a finite system of polynomial inequalities, so a la Afriat's inequality, in an observable variables and market data that observations of market prices, individual incomes, and aggregate endowments must satisfy to be consistent with equilibrium behavior of some pure trade economy. So what is going to be the technique here is going to be the technique of quantifier elimination. So that means that I'm going to be able to use techniques a la Afriat theorem, that I'm going to be able to remove infinite objects from this system. So remember that the general equilibrium consists of a nonlinear system of equations that contains infinite dimensional parameters. For instance, if you're doing a general equilibrium model, you essentially have to assume that you know the utilities of every individual, right? So how many utilities do you have to know? So you have, 10 individuals, you have to know 10 functions, right? You have to know all production functions as well. So then basically you have to know a great amount of information. So instead of doing that, we can just use shape constraints such as concavity of the utility and convexity of the preference of the technologies. And then essentially utility maximization a la GARP to be able to remove the knowledge, the need to know the utility functions, and essentially characterize what are the empirical implications of the general equilibrium model. So essentially, this is a mashup of Afriyat's inequality meets general equilibrium, okay? Now, surprisingly, nobody has done this since Afriyat inequality, Sidney Afriyat invented the Afriyat inequalities, so in the 60s, 70s, and you have to wait until the 90s. So Brown and Maskin published this paper called Testable Restrictions on the Equilibrium Manifold around the 90s in econometrica. Okay. So again, the motivation was Schoenstahl-Mantel-Debreu said, general equilibrium not good. We say, wait a moment, you were just assuming that the inputs of this machine never change. Silly you. If you move the inputs, you can do something, right? So no, thank you, Schoenstahl-Mantel-Debreu. We can in fact have testable implications. Okay. Now the setting. So I put a big name on the title. What is an equilibrium manifold? So big name, right? So who has studied differential geometry or in general, high level geometry? What is a manifold? So manifold in general, we don't need to know it at the level that a mathematician can know it. We're just gonna define what is an equilibrium manifold. A manifold is the collection of endowments and prices such that if I put them in an equation, capital F, that has essentially these two elements, F of W comma P is equal to 0. So you can imagine, right, that capital F captures a description of an equilibrium, right? So it's a machine that takes inputs and the output P and then compares them inside F and spits out a 0, right? If you are in equilibrium, okay? Now, F, of course, will capture the excess demand, right? Will be an excess demand equation. And then the W and P capture the endowments and the price, okay? So an equilibrium manifold is the collection of all endowments and all prices that together form an equilibrium. Do you understand what I mean by equilibrium manifold, right? So essentially, it's a set, right, of points of endowments and prices that if I put them inside, a system of nonlinear equations called the excess demand, or in general equilibrium machine, if I put in the endowments and the prices together, it will be equal to 0, meaning they constitute an equilibrium, right? Okay. Now, full disclosure, the notation in this chapter is consistent with the notation in Brown and Maskin, not in the notation of Mascolet. So I, of course, redefine the objects that we need. For instance, Mascolet uses Z for excess demand. Brown and Maskin use this capital F, right? Mascolet uses omega for endowments. Brown and Maskin uses the W, okay? Prices are P in both things, so it's fine. So just beware that the notation here is going to change slightly, but everything is going to be simple because we don't need that much notation, right? So just beware, I'm using a notation of Brown and Maskin, okay, in the paper. Now, Afriyat's theorem. So some, refresh of what we have seen. So Afriyat used the theorem of alternatives to prove an equivalence between of a finite family of linear inequalities that contains an observable utility levels with observable cyclical consistency or GARP. So in other words, Afriyat uses techniques from linear algebra to remove the utility function from the utility maximization problem, and essentially told us that you could have the equivalence between maximizing a utility function and having consumption data and prices that satisfies the generalized axiom of revealed preference. Do you remember this? What was the cool trick in the Afriyat inequality? It was that we didn't need to know the utility function, right? We essentially remove it from our, from our problem, and then we just we're able to rewrite the empirical content of utility maximization in terms of only of observables. So the whole thing is this. I'm going to tell you mathematically what we did in the Afriyat's theorem. In the Afriyat's theorem, we had a statement that says maximizing a utility function, a known utility function subject to a budget constraint. So this has components that are observable and unobservable. The observable components are only consumption and prices. The unobservable component is the utility function, right? The Afriyat theorem told us that this is equivalent to having the observable components, prices and consumption, to satisfy a condition called guard, right? So essentially, the Afriyat theorem told us that the whole empirical content of the utility maximization that involved an unobservable infinite object called utility function can be removed and replaced by a condition on observables alone. Do you understand? So remember the machine, right? So the first thing is these prices and consumption are consistent with utility maximization, right? From some utility that is locally not associated, continuous, and here you can associate concavity. Even only if, right, prices and consumption, which are observable, are consistent with guard, okay? Now, we want to do the same, but for different kind of observations. Now we're gonna have endowments and prices, right? And then some information about aggregate endowments. And then we're gonna be able to basically say if they come from general equilibrium. So the technique here that we use, and this is the key behind Afriyat's theorem, is called the Tarski-Seidenberg theorem. And essentially, this Tarski-Seidenberg theorem provides an algorithm which in principle can be used to carry out elimination of unobservables in a finite number of steps. So each time a variable is eliminated, an equivalent system of polynomial inequalities is obtained, which contains all the variables except those that have been eliminated. So in other words, you will see what I mean by that, but essentially we will remove all unobservables from the problem and only recover a condition that has no unobservables. That is the idea. So of course there will be some things in between, sometimes some things in between that will be useful, but at least computationally tractable. Now, this algorithm will produce 1 equal to 0. So the original system of polynomials inequalities never satisfies, so it's inconsistent. So no solution to the general equilibrium. 1 equal to 1, the original system is always satisfied, so no empirical content. And finally, an equivalent finite family of polynomial inequalities in the coefficients of the original system, which is satisfied only by some parameter values of the coefficient. In other words, so any potential model will have 3 possible outcomes. 1, the system is incoherent, right? So no solution to the general equilibrium. 2, the system has no empirical predictions. So it's always satisfied and hence void of empirical content. And 3rd, the system that I produce has an equivalent finite family of polynomial inequalities that has essentially is written in terms of data and some coefficients that are finite and that I can verify. And then a data set, if it is consistent with the family of polynomials of inequalities, then it's consistent with the model. Or if it is inconsistent, it's essentially, it can be rejected, right? The null hypothesis that the data was generated by a given system. So of course, a lot of words, we're gonna understand what's going on here. So here, I'm gonna just jump a little bit this part. We're gonna come back to this. It's kind of a summary of the technique of the proof. I'm just gonna write the general equilibrium model using an Afriyat-like setup. So I'm gonna have K commodities. This is the number of goods I have in the economy. Capital T traders. It's gonna be a pure exchange, pure traders models. Commodity space is gonna be X equal to RK. For now, I'm gonna assume that I can have negative commodities, it's fine. So we can restrict easily, for instance, that each agent has R plus K. Traders characterized by endowments. Endowments are strictly positive. A utility function that here in the notation of Brown masking is capital B, indexed by the trader, sub T, mapping from the commodity space to R, BTs are assumed to be continuous, monotone, and concave. Allocation consumption vectors are X, and then essentially have that the summation over traders of X is equal to the total endowment. So no production at this stage. The price simplex, all prices are going to be normalized. They're going to add up to 1. Only positive prices are allowed. Now, competitive equilibrium, what is it? An allocation XT for all traders and a price vector P. So remember, these traders are endowed with an endowment, right? So each XT is utility maximizing for T such to the endogenous budget constraint. Now, the price P are called equilibrium prices. What is the data we observe? Suppose we observe endowments, right? And then here, notice what I'm saying is that these endowments are indexed by experiment. So experiments run from 1 to n. And then I observe also P prices indexed by R from 1 to n. So this experiment I told you that I ran in an experimental room with 2 traders. I'm going to run them n times. So for now, to fix ideas, imagine I run 2 experiments, right? So n is equal to 2. Now, what do we observe? We observe evaluation correspondence. So given my endowments, I observe the price, okay? Now, again, a map from endowment profiles to equilibrium prices. What are the unknowns? The utility functions, right? So inside my Edgeworth box, I don't know the preferences, okay? This is the unknown utility function. Now, so the question is this general equilibrium Edgeworth box with 2 individuals, K goods, testable? The answer is going to be yes. So a pure model is testable if for every n, every number of trials, experiments, there exists a finite family of polynomials inequalities in WR, endowments, and prices for every trader and for every experiment, such that observed pairs of profiles of individual endowments and market prices satisfy the given system of polynomials if and only if they lie on an equilibrium manifold, okay? Now, before proving the testability of the pure trade, recall the Afrias theorem. So this is just a refresh of the Afrias theorem. So the theorem says, the following conditions are equivalent. There exists a non-associated utility function that rationalizes the data, P and X from 1 to n, number of experiments. There exists a non-associated utility function U such that for all I and all X, essentially, given the budget, you're a utility maximizer. Then the data satisfy what is called a cyclical consistent condition or GARP. So cyclical consistency is what Brown Maskin call it, right? But essentially, this is what we study as GARP, such that for all RST.K experiments, you have that there cannot be cycles, right? And this is essentially what I wrote here. Now, this is also equivalent to the Afriat inequalities. So the existence of numbers UI, lambda I positive such that UI less than equal UJ plus lambda J PJ, parentheses XI minus XJ for all experiments. So this, you will remember, are the Afriat inequalities, right? And finally, there exists an associated continuous concave monotonic utility function rationalizes data. So in other words, these 4 statements are equivalent. This is the famous Afriat theorem. Important, statement 1 has an infinite dimensional object, the utility function. This disappears completely in A2. So the GARP only is written in terms of observables. And then there is this intermediate output, which is the Afriat inequality, okay? So Afriat inequalities has finite parameters, U, J, and lambda J. They are not functions, they are numbers. And is written as a finite collection of polynomials, inequalities, that only depend on the observables P and X and finite number of parameters. Do you understand? So what is the magic of Afrias theorem? You go from infinite dimensional objects to finite dimensional inequalities of polynomials, okay? Is this a big deal? For sure, it's a super big deal. I cannot understate how big of a deal this is, right? Essentially, this means that you don't need to be guessing utilities. You don't need to be parameterizing utilities. You don't need to use Cobb-Douglases forever until the end of mankind. You can just get rid of all of that and just write a condition only on observables that deals non-parametrically with these things and also can be done in finite time, okay? Can be done in a computer, can be done fast, Okay, so fully non-parametric, low dimensionality. You don't have to assume any crazy stuff. Only the pure components of the theory can be assumed, and you get a full test of whether or not a data set is consistent with an economic model. So we have done this for utility functions. We know it. We appreciate Afriad's theorem. Now, let me introduce to you the version for equilibrium inequalities. Okay. So now, remember that I have n experiments, capital T traders, right? So what are the equilibrium inequalities analogous to the Afriad inequalities for an equilibrium setup? So there exist utility numbers. Remember here, there is an overline B, meaning that this is a number, not a function. For every individual, indexed by T, from 1 to capital T, for every experiment, superscript R, from 1 to N, there is lambda numbers of marginal utility of income running from every trader from 1 to T, and from every experiment, R from 1 to N. And then allocations X, and notice here in the general equilibrium setup, allocations are also unobserved. So in this data I'm imagining in Brown masking, I only observe endowments and prices. And then allocations are also part of the unknowns, okay? So I have X allocations running from 1 to T, and then experiments are from 1 to N. And then these numbers, only finite parameters, overline B, lambdas, and X's, are such that they satisfy inequalities 1, 1, 1, 2, 1, 3, and 1, 4. Who can tell me what 1, 1 tells you? So 1, 1 is very similar to what? To Afriad's inequalities, right? So essentially, this is telling you that you are utility maximizer subject to a budget, right? So this means consumers utility maximize. Now, second thing, condition 1, 2. What is this telling you? So 1, 2 is super simple, right? 1, 2 is just telling you that the marginal utility of income is positive and that the consumptions are positive. So nothing fancy here. Condition 1, 3. So remember what is observed and what is not. Endowments are observed, but X's are not observed, right? So this is just telling you, right, that your budget of each trader is endogenous, such that T in every experiment times the allocation of every trader and every experiment is equal to the price of every experiment times the endowment of every trader in every experiment, right? So in other words, this is just the budget, endogenous budget equality, right? Do you understand? So remember here, what is observed? Endowment and prices. What is unobserved? X, right? And then finally, this is the easy one. What is this?
Is that everything gets consumed overall?
Market clearing, right? Okay, so essentially, this is the nice thing about Afriad inequalities. We have rewritten the conditions of world rational equilibriums into Afriad inequalities. So one tells you that every consumer utility maximizes subject to their endogenous constraint, right? And with market clearing. Now, so are you convinced this is a general equilibrium situation? Yes. Now, what is new? What is different from anything that you have seen in macro and anything you have seen before? That this thing here, right? You can put in MATLAB right now. You can write, right now this system of polynomials, and then you will look for V's, lambdas, and X's. And then if your collection of endowments and prices pass these inequalities, then you know they come from a general equilibrium situation, meaning that every individual inside the Edgeworth box is utility maximizing, is a rational agent, and is utility maximizing, right? Subject to endogenous budget constraint, and is able to convert endowments into the observed prices, okay? Great. Now, important thing here. What is this doing? So this is relating endowments to prices within the machinery of general equilibrium without knowing the parametric restrictions on the utility, right? So this is a big deal, okay? Now, turns out, remember that we did predictions using GARP. So remember that GARP did the same thing, but for utility maximization. There, what was the input? It was a budget, right? And what was the output? It was a consumption, right? So the data was different. And then essentially GARP and the affiliate inequalities related budgets to consumption, right? And then given the GARP, you could do predictions out of sample, right? So essentially, what this machine will do is that I can take an out of sample endowment and then I can predict what is the out of sample price given this out of sample endowment, right? And then essentially what I have to do is use these inequalities to bound to create a set prediction of the out of sample price. So this machine here will produce prediction of prices, okay? And it also constitutes a test of whether or not the observed endowment and prices from your experiment comes from general equilibrium, okay? Now, everyone understand what's going on? Now, remember the question, what was the motivation of the chapter? Schoenstahl-Mantel-Debreu told us that anything goes. So we have obtained now a set of inequalities that given endowments and prices, tell us whether something is consistent with general equilibrium, right? What is missing? We have to create one data set, one counterexample of Schoenstahl-Mantel-Debreu, okay? We will create one data set that will be inconsistent with these inequalities and hence will violate the general equilibrium inequalities, okay? So counterexample, so here.
So Victor, you are saying that you have to impose like to derive like a necessary condition to test whether.
So this, wait. So these are necessary and sufficient conditions, if you remember, right? Because the same as affiliate inequalities, these are necessary and sufficient. So I have derived necessary and sufficient conditions. Now I'm gonna produce a counterexample. And here I have it. Okay, so
we use the part of the necessity in order to use it as a test for general equilibrium, right?
Yeah. So I'm gonna go now to the iPad. So I show you a counterexample. Okay, so let me share quickly. iPad. Great. Perfect. Okay, so first of all, we have here, right, an Azure box of size 1, right? And then in this Azure box with consumer 1 and 2, right, there's going to be some endowment, price, vector, right? And for instance, you're going to have this, right? And now, you can also have a second Azure box with a different endowment, right? And then here I'm going to do something like this. So this, I can do it actually this way. So I'm just going to throw now the price, it's easier. So here, I'm just going to have a different price, right? With a different endowment point. And then essentially, these two things are price P1, right? With endowment W1, and price 2 with endowment W2, right? And this price 1 endowment W1 comes from Azure box 1, right? And you can imagine a translated Azure box where this second price arises, right? I cannot draw it just for clarity, so I don't get too many lines. This is my data. So essentially I have hyperplanes that pass through a point. This is the data. I have two observations now, okay? So my data here is W1 P1 and W1 P2, okay? Now the question for you, is this data consistent with general equilibrium or not? The answer is gonna be no, obviously, but the real answer I want is why. So essentially, remember that any point inside this supporting hyperplane can be an acceptable allocation, right? So I'm gonna change to red, for instance. So imagine, for instance, this allocation here is one possible allocation consistent with X1. I'm going to call it X1, right? And this allocation here is consistent with X2, okay? With the omega 2, W2 and price 2. Now, in fact, any other allocation around it are also consistent, right? Because remember that here X's are not observed, okay? So I'm just picking two particular ones, okay? Out of the many ones consistent with this. Now, what is wrong with these things? So look at this, X2, right? X2 is reveal preferred to X1. Do you realize why? Under the P2 budget, right? X1 is affordable, right? But X1 is peak. Yes? Everyone sees that? So X1 is affordable under P2, is below P2, but X2 is peak, right? So X2 is really preferred to X1. Okay? And also you have here that X1 is reveal preferred to X2, right? The same thing. Under P1, the other budget, X1 is peak and X2 is affordable. Okay? So what's up with this? Essentially, this creates a cycle, right? So this means that these two data points cannot be produced by general equilibrium because there are allocations consistent with this price and endowment such that they violate the weak axiom of reveal preference. Okay? And then, I'm done. So this is a counterexample of general equilibrium. So these two prices and endowments cannot be possibly generated by two consumers that are utility maximizers and that live in an edgeward box, right? Do you understand? What is the key here is that I remember that what allocations are consistent with this. Well, any allocation that is inside the box, right? So in fact, right now, so this is done. Now I'm gonna use another color, green, to show what allocations are consistent with this. So anything that is inside the box that passes through endowment, right, is consistent, right? So any X1 here could have worked, right? Because all of them are consistent with the price and endowment. But of course, it was enough to find one X1 that did the job of basically saying that this is not compatible with the model. Okay, any questions here? Okay, so no question. Great. So the whole point here, and this is the file that I will reestablish this later before real uploading the notes. It just says that finding a counterexample of inequalities means that your model is testable. Okay. So this is the answer to Schoenstahl-Mantel-Debreu. So in Econometrica, you go and you will find a drawing by Donald Brown and Rosa Maskin. It's essentially similar to mine. And that constitutes a full proof, right? Why is a full proof? Because finding a counterexample, right, is enough to establish that general equilibrium has testability, right? Is testable, okay? And testability is a property. Do you understand? So the fact that there is at least one simple data set with two observations, right, that violate the inequalities means that not everything goes, okay? So a big deal. So important thing here, econ makes progress. Schoenstahl-Mantel-Debreu thought for a long while, and everyone in the profession thought, and even now. So if you ask some of your professors, they will still tell you anything goes, right? It's not true. It only depends on the variation of omega. If omega changes, then you can test these things with a data set of prices of omega. With at least two observations, you can test general equilibrium. Okay? Now, important thing here. Okay, so I have told you all of this. Now you tell me, and you have to ask this question. So is this useful? So you have to ask these things, right? So I remember one time when I was in grad school, one of our classmates, the professor was discussing continuity within an expected utility model. And the student asked, but why do we have to assume continuity? And the professor got super mad. I think he got a bad day. But these questions are in the end, important, right? So why in the world do we care about this? So this seems to be an interesting description of a pure exchange situation, right? Which means I run an experiment, I am an experimental guy, I run this experiment many times, and then I can test whether or not this collection of endowments and prices are consistent with general equilibrium, meaning that every individual maximizes their utility subject to the endogenous budget constraints and everything markets clear, okay? Now, the important thing for you is the following. So if you're a macro person, then this should teach you at least one thing. It should teach you that you shouldn't do really macro with time series, right? Because again, especially within small time frames, your endowment is not really changing, right? You need variation in endowment with stable preferences and technology. So in a typical time series situation, you're at least breaking two conditions. First, technologies most likely are changing. I don't know about preferences, maybe they are. But for sure, technology is changing. But more important, endowments are not likely to be changing much. So usually endowments are thought to be the very fundamentals of the economy, right? So initial resources and so on. We know there are structural breaks, but whenever there is a structural break, such as, Ecuador have a new finding of more gold, that usually happens in these countries, right? So you find a new mine deposit, right? Huge one of gold, then this means a structural break. The country updates their endowment thing, and now the economy changes the new situation. But that means you only have two observations, right? So in time series, you have as many observations as the structural breaks, okay? So remember that. Now, macro people are not, they are smart. So they essentially internalize these issues, and they realize you need some endowment change. So how do you obtain endowment variation? Well, by using, first of all, as I told you, in the revolution of late 90s, 2000, the cross-sectional data from countries, right? So they stopped using cross time series data from one country, and they start using cross-country data. So what was the idea? Well, obviously there is variation in endowments because you're pulling data from Ecuador, and then you're pulling data from the US and pulling data from Japan. So obviously there are variation in endowments. So this will give you the stability, and hence it means you can actually identify and predict prices. But now, what is the really modern way of doing macro? Well, using microdata. So, for instance, one particular sub-branch of macro is studying renting markets, housing markets, right? And that's kind of an ideal situation because you can define local markets by location, right? So, for instance, you can say North London is one market for housing, right? And then South London, and then of course Toronto area, that's another market. So you have as many markets as locations with kind of a demand con. And then after defining markets, which is not easy, you essentially have variation in markets, right? So for instance, London has more space, has access to creeks, to rivers, nice walks. Toronto has more urban services. You get more cafes, you get more shopping malls, whatever, more public transport. All of that is an endowment, right? Well, of course, in North America, choosing a high school or a primary, especially primary for your kids, right? So each neighborhood has a quality associated with the school there, right? So that's a big deal for North Americans, right? Because they are not allowed to take their kids very far away. So they also have to choose, that's part of the endowment of the location. So all of that constitutes the endowment of the location. And then, of course, you'll have different prices per neighborhood, right? Average price per neighborhood varies. And that's essentially a classical example of this theory, right? So you have endowments, and then you have prices. And then essentially using these kind of inequalities, you can study and predict what would be the new price, given the new endowment, right, in the urban market. Now, so what I'm telling you essentially is that you can easily adapt this idea to real life situations, right? And essentially the second thing I'm telling you is that in order to actually do econometrics with general equilibrium, you have to have variation in endowments. So you have to have some spatial variation due to market variation, right? And this spatial variation can be rather extreme, like country variation, or you can have micro variation, but usually location variation. So in general, I think location or spatial variation is one key form of which to obtain this kind of data, right? And essentially a lot of macro people are using now spatial data, so micro data with a lot of variation, okay? So any questions here? Of course, the other kind of data you can obtain is experimental data, which is cleaner, right? Yeah, Martin?
Yeah, two questions. So first of all, is it reasonable to assume that preferences and technology remain unchanged?
Yeah, I agree that. So again, for me, preferences, I think actually is a very good assumption that your preferences are stable. What is usually not reason. So imagine first you have a cross section of time, right? So I'm studying the housing market today after the pandemic. So imagine it's a more normal year, so 2022, right? The pandemic is gone, and then essentially, you study that so in a cross section, and then you can assume essentially that every consumer is looking more or less for the same, right? And then for instance, in the housing market, you have to assume that all of them are a separate utility that values things differently. And then, of course, they are put in different situations with different trade-offs and they choose differently. Now, you have to deal in reality, if you're doing this empirically, with selection issues, right? For instance, and then this will break the assumption that Martin is pointing out. For instance, the people that live in London, do they have the same preference for housing that the people in Toronto? Well, it's doubtful because there's a lot of people that like big yards, a lot of less traffic. They will migrate to London, right? So there are some issues with the exogeneity assumption. So essentially, this model is done under exogeneity, right? What you are saying, Martin, is essentially a form of endogeneity that preferences depend on the market, right? So essentially, for instance, people that like green big yards, they will go to London, right? And if people like really good espressos, they go to Toronto, right? So essentially, this assumption may be reasonable sometimes, but sometimes you need to do some work, some additional work, and then you have to redo this statistically, right? So you have to add these numbers should become random variables, and then you have to deal with endogeneity of these random variables with the market. So it can get complex if you try to apply it. But yeah.
Okay, yeah, I was asking about specifically not variation in preferences across different locations, but over time.
Yeah,
like
so that's important. For instance, if I'm running an experiment and if I run all my trials the same day, I wouldn't be worried that your preferences are really changing, right, within a day. Now, if I study a long panel of a household and I follow this household for 10 years, then possibly your preference when you are 10 years younger are different from 10 years later, right? So this is all application dependent. So this is, of course, a textbook treatment, will give you a benchmark way of doing things. And then, of course, if you try to move this to reality, for instance, if you're working on job market paper 4 years from now, then, of course, you have to also deal with dynamic choice, right? So how, choice changes in time and how, habit, for instance, modifies your preferences, right? So that's for sure something to take into account. So both assumptions that you're stable in time and stable in a space might not be appropriate given certain applications, right? And yet again, this is a textbook treatment where this is telling you kind of a benchmark situation. And it's giving you that a strong message that yes, you can do parametric analysis just using the assumptions of utility maximization and market clearing, within a computationally feasible framework. And then, of course, implementing this in real life and taking into account whether all these assumptions, especially the stability of preference and technology, as Martin well identified as the main assumption here, is well suited for the given application, right? And most generally, it will not be, and then this will constitute a job market paper, right? Because you were able to deal with that particular extension to make it realistic for the given data that you have, okay? And that's, the way to go. But right now we're going to study just the in the void nice ideal application, okay?
Okay, perfect. Another question. So after testing for the consistency with general equilibrium, does this give validity to future predictions of prices?
Yeah, for sure.
Okay.
Yeah, so right now I'm gonna stop the recording, right?